So exercise related to star in the solar system. The first 7 questions we did. We'll start with question 8. Which planet in our solar which planet in our solar system is nearest to the sun, and what is the nature of this planet? So we have like Mercury, Venus, Earth. So Mercury is the closest one, and what is the nature of the Mercury? It's a rocky. Mercury, Venus, Earth, Mars, these are the rocky planets. And then we have the gas giants, Jupiter, Saturn. In question 9, a space station orbits Earth at a distance of 7,000 kilometers from the center of the Earth. We always take for a orbital speed, we always take a distance from the center. So from center of the Earth, the distance is 7,000 kilometers. And it makes 50 orbits in 24-hour period. Like 15 times it orbit in one day or 24 hours. What is the speed of the station? So how to work out the speed whenever object move in a circular path? So speed is distance divided by time, or it is equals to the circumference. So circumference, which will be 2 pi r divided by t. Now 2 multiplied by 3.14 multiplied by radius. So what is the radius? That is 7,000. So we write 7,000. This is 2 pi r divided by t. So how much time it will take to complete one orbit? This is a time for 50, like 15 complete orbits, 24 hours. So 15 orbits are there, or 15 revolution. You can also say that 15 revolutions are there in 24 hours. One revolution will be x. We just cross multiply. So x will be 24 divided by 15. So it will be 24 divided by 15, that because that will give us the time for one revolution. And the total distance in one revolution equals to the circumference. So when we multiply 2 into 3.14 into 7,000 and divided by 24 divided by 15, we get 27,000 kilometer per hour. Is it clear, this one?
Yes.
Yeah.
Okay. In question 10, which nuclear reaction powers a stable star? First, what is the meaning of a stable star? A stable star will have the gravitational force balances with a radiation pressure which is outward. And the stable star does not change the size. So as a stable star does not change the size,
This is the main sequence.
it's a main sequence star. So nuclear fission, first thing, fission is wrong because for the stars, nuclear fusion happens. So either C can be an answer or D. But it's a nuclear fusion of the hydrogen. First, a hydrogen fusion is there, and then the helium fusion. So in a main sequence star, which fusion is there? That we have a hydrogen fusion. That's why option D is a valid answer. If we turn into a red giant or a supergiant, then a helium fusion will start. Question 11. Which stages in a cycle of the star are listed in order they occur? So first, what we have when we check the options, first we have like interstellar cloud, but then from interstellar cloud it will turn to a protostar. So this order is not correct, not stable. So this order is not correct. Protostar, from protostar it will turn into a stable star. So this order is not correct. It's written red giant. Red giant, it turned into a white dwarf, and white dwarf to a protostar. That is again wrong, because red giant, it will turn into a white dwarf, but like planetary nebula and white dwarf, but not turn into a protostar. So stable star turn into a red giant, and then red giant turn into a white dwarf. That's why D is the correct order of the stages of the star. And this is about the low mass star. If it was a high mass star, then from a stable star, it will be a supergiant, then supernova, which may leads to a black hole or a neutron star. In question 12, which statement about the solar system is correct? All planets are rocky. No, that's not correct. We have the gas giants as well. Only Earth has a moon. That's also wrong. Other planets have the moon as well. Like Jupiter is also having moon. Pluto is a dwarf planet. Yeah, that's true. That it's a dwarf planet. And there are many stars in the solar system. This is wrong. There are many planets in the solar system. We have the one star, which is our sun, and all the planets are moving around. So in a universe, there are millions or billions of stars, or in a galaxy also it's a combination of stars, but not a solar system having only a one central star around which the planets are moving. So that's why option D is incorrect. Question 13. Comets are bodies which orbit the sun in the solar system. What is the shape of the orbit and how the sun positioned within the orbit? So if this is representing the sun and we draw the orbit of the comet, that's how we draw. So it's not circular, it is elliptical. So either C can be an answer or D can be an answer. And then the center of the orbit, the center of this ellipse is not the sun. For comets as elliptical, at the center we don't have the sun. One part, like there's a focus of the ellipse, there we find the sun, but not at the center. That's why option D is the right answer. In question 14, which nuclear reaction produced the release of energy to power a star? So how the stars are producing energy? When we check the options, a nuclear fission, wrong. Because for stars, it must be a fusion, like a lighter nuclei joined to form heavy. A nuclear fusion of a helium into hydrogen, that's wrong. Because if fusion happened, the lighter nuclei turn into heavy. So hydrogen is 1, where helium is 4 and 2. So hydrogen turned into helium, not helium turned to hydrogen. That's why option D is the right answer, in which the hydrogen turned into helium. Question 15. What is the definition of a Hubble's constant? So how we define the Hubble's constant? First, what about the Hubble's law? Hubble's law states that the recession speed at which the galaxies are moving away from us, is proportional to the distance of the galaxies from us. Like further the galaxy, the faster it moves. And the formula for Hubble's law, V, the speed of the galaxy, is a Hubble constant into D, or V over D is equals to H naught. So Hubble constant is actually a ratio between the speed at which the galaxy is moving and the distance. Or Hubble constant is also a reciprocal of the age of universe. Like H naught is 1 over T, or T is equals to 1 over H naught. So either it can be refers to the reciprocal of age of the universe, or it is a ratio between speed and distance. Both are acceptable. So when we check the options, the ratio of the speed at which the galaxy is receding from the Earth to a distance, so that's right. Like ratio between speed and a distance, we call that as a Hubble constant. What about other options? The value of a change in the wavelength of a galaxy starlight due to a redshift. This is called a Doppler shift. This is not called the Hubble constant. This is called a Doppler shift. The constant used to represent the rate of expansion in all the direction, no. Estimated constant equal to age of universe. Why this statement is wrong? It should be reciprocal to the age of universe, because Hubble constant is 1 over T. So it's not equal to age of the universe, it's reciprocal of the age of universe. This statement can be correct if it was written estimated constant equal to the reciprocal of the age of universe. So this statement is also wrong. That's why A is the right answer. Is it clear?
Yes.
Yes, sir, clear.
Then we have question 16. Which row about the orbit of the Earth and the Moon is correct? Like approximate time for the Earth to orbit the Sun. So it's like 1 year, which is equals to 365 days. And for Moon, it's 30 days or 1 month. So that's why D is the right answer. Which statement about the orbit of the comet is correct? So it's a similar question. The orbit of the comet is elliptical, where Sun is not the center. So when you check the option, because similar questions are there, so comet is elliptical and Sun is not at the center of the orbit. Which row describe the power source of the stable star? So nuclear fission is like when a heavy breakdown into lighter. So it happened a nuclear fusion, and which fusion happened? The hydrogen fusion happened. That's why C is the right answer for this. Question 19. Which quantity can be determined by using the brightness of a supernova in the galaxy? Like the supernova is explosion which produce a star light. And this light, using this light, what we can do? We can work out the Doppler shift. Like how much uh, the shift happen or occur. And from that Doppler shift, so which quantity can be determined using the brightness of the supernova in a distant galaxy? A supernova explosion is producing a light. So what we can use it using the supernova, like how we know the speed of the light and how much time it is taking. So using that, we can determine the how far this galaxy is from us. So speed at which the galaxy is moving, speed at which the galaxy is moving, using a redshift, we can work out that. But from the brightness, we can know like how far this supernova happen or occur from the distance of a galaxy from the Earth. So that we can measure. Hubble constant, it's a reciprocal of the age of universe, and age of the universe using a reciprocal of the Hubble constant. So if they, for example, if there was the same question, but they change which quantity can be determined by using the change in the wavelength of a supernova. So if they change in the wavelength, then what will be the answer? In that case, A will be the right answer. So using a change in wavelength or a redshift, we can determine the speed at which the galaxy is moving. But using the brightness, we can determine how far this galaxy is from us. In question 20, Pluto is a dwarf planet. Figure 10.1 shows the direction of the motion as it's elliptical, as you can see the orbit. At point X is the point of orbit closest to the sun, and Y is further. Orbital speed of a Pluto varies. Describe how the speed of a Pluto varies when it moves from X to Y and then back to X. So moving from X to Y, because if the distance increases, the kinetic energy will decrease. So the speed, when it is moving from X to Y, the speed will decrease. And moving from Y to X, from position Y to position X, so what happened to the speed? The speed will increase. Explain terms of energy, why this speed vary. So a structure answer for this one. First thing you will mention the total energy is constant or conserved. So what will happen? The total energy is a sum of the gravitational potential energy due to the position and the kinetic energy due to the motion. So when it moves closer to sun, the height decreases, so GPE decreases. So the kinetic energy will increase. And as it moves away from the sun, the GPE increases, the gravitational potential energy, energy due to the position, and the kinetic energy will decrease. So you have to refer these points as structure answer for explaining the motion of the planet around the sun. So one, like first thing you will mention about the gravitational potential energy, which is a constant, like the total energy is conserved. So gravitational potential energy plus kinetic will be constant. So when it moves from one position to another, the potential energy increases and the kinetic energy decreases. And other way around, potential energy decreases and the kinetic energy will increase. The average temperature of the surface of the Pluto is 43 Kelvin. Convert the temperature into Celsius. So there's a conversion. You have to learn this conversion. Temperature in degree centigrade is equals to temperature in Kelvin minus 273. So if you want to convert the Kelvin into centigrade, we subtract 273. So this one is 43 minus 273. So when we simplify this, we'll get as minus 230 degrees centigrade. And opposite, if we want to find in Kelvin, to convert the degree centigrade, we add 273. So this is a conversion from Celsius to Kelvin, and this conversion is from Kelvin to Celsius scale. Pluto has a white surface as shown in figure 10.2. As a Pluto rotates, the white surface alternated face towards and away from the sun. How they affects the temperature of a Pluto as it rotates its own axis. So if it is rotating in its own axis, as you can, if the white surface is facing the sun, white surfaces are good reflectors, so it will reflect most of the energy from the sun. So the temperature will not increase too much. But as it rotates, when the black surface is there, as it rotates, so it is a good absorber. As a result, what will happen? The temperature of the Pluto will increase. So on the white surface, increase in temperature is smaller as compared to that of black surface, which is a good absorber of heat radiations. Question 21, state the equation that defines the average orbital speed, and any symbols you use, state the meaning of any symbol. So we use V is equals to 2 pi r divided by t. And what is the meaning of r? R is the radius and t is the period or the time period. Suggest why countries that are significant distance from the equator experience a significant variation in temperature throughout the year. So what is the reason why for those countries which are having a greater distance from the equator experience different seasons or change in temperature? So that is the main reason is the Earth axis is slightly tilted. The Earth axis is not exactly vertical, it is slightly tilted. So the countries, for example, Northern Hemisphere and the Southern Hemisphere. So what will happen? So Earth axis is slightly tilted. So amount of radiation which is received by the countries in the Northern Hemisphere will be different from the Southern Hemisphere. So as a result, and you can also say the duration of the day will be different. Like the countries in the Northern Hemisphere, as it is facing the greater amount of energy received from the sun, so duration of the daylight will be longer as compared to the countries in the southern hemisphere in this position. And after the 6 months, like when it is on the opposite side, the southern hemisphere countries will experience greater amount of radiation or receive greater amount of radiation. So the duration of the day will be longer for southern hemisphere than the northern. So the simple answer for this question, you can just mention, as Earth axis is slightly tilted, so the countries receive different amount of energy throughout the year. That's why it causes a change in temperature. Fill in the gaps in the paragraph about the star are much more massive than the sun. The stage of a star that follows the stable state in a life cycle, so the stage that follow the
Old,
state, yes,
old stage.
okay, but the gaps about much more massive. The stage that follows the stable star in a life cycle means for a massive stars, the massive star from main sequence, from stable star, they will turn into what? They will turn into supergiants. Like when we have a main sequence star, you can say red supergiant or you can also say supergiant. So from a main sequence star, it will turn into a, or from a stable star, it will turn into a red supergiant. It then explode as a supernova to form. When supernova explosion happen, that things which is also known as like a nursery for the star called a nebula. So as a result, it will form a nebula. And this leaves behind, what the nebula leave behind? It will leave behind a black hole or a neutron star. So the supergiant turn into an explosion, supernova happen, and because of that supernova, the things we call a nebula is also like nebula is also the like a start of a new star can form in that region, but that may turn because of the high mass, very strong gravity, it might turn into a black hole or a neutron star. A galaxy is moving away from the Earth with a speed of 33,000 kilometers per second. The value for the Hubble's constant is 2.2 exponent minus 18 second inverse. Calculate the distance. So we have the formula, the speed of the galaxy is Hubble constant times d. But we need a light year. First we determine in kilometer and then we can convert into light year. So speed of the galaxy is 33,000 kilometers. The Hubble constant is 2.2 into 10 to the power minus 18. And d is a distance. This will go there in division. So 33,000 divided by 2.2 into 10 to the power minus 18. This will give us the distance of the galaxy in kilometer.
One 1.5 into 10 power 22.
So 1.5 into 10 to the power 22. That is in kilometer.
Yes.
Okay. Now, or if we convert this in distance into meters, so we multiply by 1000, so this will become 1.5 into 10 to the power 15. Okay.
How?
This is kilometer because this is given in kilometer per second and this is given in second inverse. So when we simplify this, the answer is in kilometer. So kilometer into meter, if we want to convert, we multiply by 1000. So 1.5 exponent 22 multiplied by 1000. So you got 1.5 exponent 25.
Yes.
Now, there is a relation which you have to learn. Like one light, because we want to convert the distance into light year. One light year
Yes.
is equal to what? One light year is equals to 9.5 into 10 to the power 15 meters.
Yes.
So one light year is this much meters. If we have 1.5 into 10 to the power 25 meters, how many light years are there? X cross multiply. So it will be 1.5 into 10 to the power 25 divided by 9.5 into 10 to the power 15. What is the answer for X? You have to memorize this.
150
Yes.
million light years. 158 into 10 power 6.
158 into 10 to the power 6. Okay. So 158 into 10 to the power 6 light years. It will take approximately 156 or 158.
It was showing 157.5.
Okay, it's okay, that's fine. Into 10 to the power 6. Okay. Check the digits because one of the digits is missing. Usually, like this answer is about 1.5 into 10 to the power 9 light year. So one of the digit maybe is missing. 1.5 into 10 to the power or 1.56 or 58 into 10 to the power 9 light year. But this conversion is important. So what you did, like you can even convert this speed into meter per second. If you want to convert into meter per second, you multiply by 1000. So when you multiply by 1000, so this will be so when you multiply by 1000, this will be the speed divided by 2.2 into 10 to the power minus 18. This will give us the distance of the galaxy in meter. What's the answer for this? This will be in meter because we directly convert this into kilometer per second into meter per second multiplied by 1000. What's the answer for this? In exponent. And the final distance, yes, Hamid, Saim, what's the answer?
I'm doing it.
So V is equals to H naught D. And then always use one light year. This you have to memorize that one light year is
1.5 multiplied by 10 power 23.
1.5 into 10 to the power 23. Okay. So this is 1.5 exponent 23. And then we have one light year is this many meters, like 9.5 into 10 to the power 15 meter. So if X light year, how many meters? 1.5 into 10 to the power 23. So when you cross multiply, the value of X will be 1.5 into 10 to the power 23 divided by 9.5 into 10 to the power 15. When you divide, this will give us the value for the distance, which will be about 1.58 into 10 to the power 9. That is the right answer. So you have to memorize this light year. One light year is equivalent to how many meters? Is it clear?
Yes, sir.
Okay. Next question is figure 9.1 shows the sun as a center of dot and the planets Saturn, Jupiter, and Earth are labeled like they're in line. Assume that the Saturn takes 30 years to orbit the sun, Jupiter takes 12 years, and Earth, as you see, it's taking. On the figure, mark the position of a Saturn and Jupiter 5 years after the original position and label that as S1 and J1. How this can be done? This can be done with a measurement as well. Like one complete revolution, like for a Saturn, it takes 30 years to move around the sun. Means one complete revolution is equals to 30 years. You can convert that into angles as well, like with a measurement with the angle. Say, when we talk about the Saturn, for a Saturn, 30 years it take for one complete revolution or 360 degrees, because when it will be at this position again, it will pass 30 years. So we want the position after 5 years. So 5 years, how many degrees will be there? X cross multiply. So what is the answer for 5 years? When you cross multiply the value of X?
60.
Yeah, because 30, so we just cross multiply. So the answer for this one will be 60 degrees. So you can place your protractor here, like place your protractor. Then this will be 10, 20, 30, 40, 50, 60. So where you get 60 degrees, you mark a position and that we call as S1. Is it clear? Because we want, this will be 60 degrees. From the original position, it will be 60 degrees. So this will be the new position. We don't have to draw this line, but we need a position for the Saturn. Same thing for a Jupiter, how it can be done? For a Jupiter, it takes 12 years. So 12 years it take for 360 degrees. 5 years it will be X cross multiply. What's the answer? So it will be 360 multiplied by 5 divided by 12. What's the answer for X? How many degrees?
150.
150. So again, you will place your protractor here in this manner. Okay. So this will be 0. This will be 0. Then 10, 20, 30, 40, 50, 60. This will be 90. So, but we need, it's a more than 90. It's like 150. So this will be 100, 110, 120, 30, 40, and 50. So 150 example here. So what will be the position of the Jupiter with reference to this? So the Jupiter will be here. So J1 will be the position of Jupiter.
Yeah.
So if you want to show the position of the Jupiter, Jupiter will be somewhat here and the Saturn is there. Is it clear?
Earth after 5 years will be at the same place.
After 5 years, no, not same place. Jupiter started from here, J0.
Earth,
After 12 years, it will be at the same position.
Earth would be at the same place after 5 years.
Which one?
Earth.
Earth will be the same place because, yeah, that's right for Earth, because one complete revolution for Earth is 1 year. So after 5 years, it will be on the same position. So we don't have to change the position of the Earth. And in the question, we need S1 and J1. So that's why. Is it clear? This one? How we work out the
Yes.
position?
And more time.
Yes?
Can you explain?
Yeah, sure. See, the Saturn take 30 years to completely orbit the sun. So means 30 years, in 30 years, how many degrees it will cover? Because one complete revolution or 360 degrees in 30 years. We want in 5 years. So in 5 years, how many degrees will be there? X. So cross multiply. So it will be 360 times 5 divided by 30. That will be the value for X. So when we simplify this will be 60. So Saturn will cover 60 degrees from the starting position. So we place a protractor here. This will be the 0. Then 10, 20, 30, 40, 50, 60. So where we get 60, that will be the position of the Saturn. We call S1 on the orbit of the Saturn. For the Jupiter, they mentioned the Jupiter take 12 years to completely orbit. So 12 years makes 360 degrees. Like in 12 years, it will complete the orbit, so 360 degrees. We want the position in 5 years. So 5 years, what will the angle X? When you cross multiply, you will get 150. So 150, again, you place a protractor here. Mark 150. So this is 0. The 10, 20, 30, 40, 50, 60, 70, 80, 90 will be here, the perpendicular. Then 110, 120, 130, 140, and 150. So this will be 150. So 150 is here. So the position of the Jupiter will be on this side. Is it clear? The position of the Jupiter?
Yes, sir.
Then on the figure, mark the position of a Saturn and Jupiter 20 years after the original position. And that is S2. For Saturn, 20 years after, so the same way, we know for what is the orbital, like 30 years, 360. So 20 years, it will be X. Cross multiply, you will get the angle. So 360 multiplied by 20 divided by 30. This will give us the angle, which is about 240. So 240, because this angle is 180, 180 will be here. Because one complete angle of a protector is 180. So 180 here, then we'll measure from this side. 190, because we'll change the protector position because half is 180. So 190, 200, 210, 20, 30, 40. So 240 somewhat here. So we write that is the new position of the Saturn. Is it clear? Because this is 0 degrees. This will be 90. This will be 180. This will be 270. And again, this will be 360. So means if the angle is 240, so which region will have the angle in this, like position in this region. If the angle was from 0 to 90, it will be in this position. 90 to 180, this position. 270 to 360, it will be at this position. Is it clear about the Saturn?
Yes, sir.
Okay, I'll share another link and we'll continue this.